All right. Hi, everyone. Right now, we are going to do Arrhenius acid-base theory. So we kind of already knew what acids and bases were. And then we have the scientist Arrhenius come in, and he gives us like a chemistry definition that goes beyond our regular real-life definition. So let me move the bubble. Move the bubble. There we go. All right. And I need my pointer. There we go. All right. So prior to the Arrhenius theory, we just identified acids as things that tasted sour. So you can think of like a lemon, for instance, that's citric acid that makes it taste sour. So acids, according to Arrhenius, he comes in with this final definition here that when this covalent substance is ionized by water, meaning water attacks it and pulls it apart, the H plus, called hydrogen ion, is the only positive ion that appears in your solution. And when you have hydrogen ions in your solution, that's going to make the pH of your solution be less than 7. So you can watch the pH video later after this, but the pH scale tells us essentially how strong our acids or bases are, and it runs on a scale from 1, some people say 0, to 14. So acids are on the low end of that scale, and neutral is 7, and then our bases would be the high end. So bases are things that taste bitter. For us, that would be soap. Soap is a base that you know of. You've probably gotten soap in your mouth just from being a human, washing your face. It happens. Because bases are ionic, they dissociate in water. So water, dissociation and ionization are, in this case, very, very, very similar, but it's just important to realize that if it has ionic bonds, more likely it'll be a base. And if it has covalent bonds, it would be an acid. If you're asked to identify an acid or a base just from each other, it does not mean that all covalent things are acidic or all ionic things are basic. That is not true. But all acids are covalent. And all bases are ionic. But the converse is not true. Not all ionic things are acids. So bases are ionic. They dissociate in water. And when they dissociate, we get the hydroxide ion as our only negative ion, according to Arrhenius. So Arrhenius bases, I like to start here because I think it's a touch easier. Again, they are ionic. And when they dissociate in water, they produce hydroxide ions, or OH minus. Now, the more OH minus that we get in our solution, the stronger the base is. It's a strong base. So our strong bases are going to come from group 1 and group 2. Those are the metals. So for instance, potassium hydroxide would be a strong base. And the reason for that is because it's very soluble, and that makes the hydroxide very available when it dissolves in water. That's the best way I can put it. Here, magnesium hydroxide. These break up very, very well, so that makes this hydroxide ion free to swim around, and that makes it a strong base. I hope that makes sense. Acids, again, they're covalent, and instead of being dissociated, they're ionized by water, which really just means that they're attacked by water. They yield or give us a hydrogen ion when they dissolve in water. And there's no real area on the periodic table that's like, these are your strong acids. It's just kind of like scattered around. I believe the New York State reference table, it's K and L, I believe, are your acids and bases, and it will tell you their names. So for reagents chemistry, you don't need to know how to name them. I'm just checking my notes. Yes, because table M are the acid-base indicators. So J, K, L, M. Yes, it's K and L. K and L are your acids and bases. H2SO4 would otherwise be named hydrogen sulfate. That is actually sulfuric acid, and that's a strong acid. So that's hydrogen and a polyatomic ion. And then sometimes you can have hydrogen with just like a regular ion. So the members of group 17 like to make acids. Fluorine, not very strong, but chlorine is very strong. So it kind of depends. You can't just say like a particular group on the periodic table is going to give you strong acids, but different things around the table will. Okay. I think the most important thing here is that all acids and bases are going to be electrolytes when they are aqueous, meaning they're dissolved in water. The reason for that is because you get these hydrogen ions or your hydroxide ions that are swimming around. And when you have mobile ions, your solution will be able to conduct electricity, and that's what makes it an electrolyte. So, refresher. Can I go backwards? Oops. Acids taste sour. They have a pH of less than 7, and they give us hydrogen ions as our positive ions when they are dissolved in water. Bases do the opposite. They're bitter. They have a bigger pH, and they give us hydroxide as our negative ions. And then we have this, let's say, is hydrochloric acid. So this right here is a hydrogen, and this would be chlorine. If that's the case and we're dissolving it in water, one of these water molecules is going to steal the hydrogen, and that is going to create this, which is H3O+. This is a hydrogen ion plus the water molecule. We call it hydronium. It gets a new name. And it also acts as an acid ion. It's really just the acid ion and water stuck together. It is sometimes called protonated water. So this is how acids work, really. But sometimes you'll have it just be written as H+, ignoring the fact that it's attached to water. And then sometimes you'll have it written as H3O+, which is the two of them combined. It's really just interchangeable and depending on who writes it. But this is why we say that acids are ionized. It's because the water steals the hydrogen, where for bases, they just break apart and float around. So that's the main difference. And that's all. Feel free to rewatch the video or leave a comment if you are confused or need some questions answered. I'll talk to you soon.